Okay, so here's where we were last time. We were talking about path independence. And where we ended last time, let me start off by reminding you what path independence means. It means that when you have two curves that start at the same point, two curves must also end at the same point, then amazingly, a vector field that has this property of path independence, the line integral along the one path and the line integral along the other path would have to be equal. And it seems a little bit outrageous to suggest that, how could this be? What could the vector field possibly do to have a computation done all the way over here always line up with a computation that's done all the way over here? Right? It doesn't seem realistic. The computations are done on different sets. I mean, surely the vector field over here would be unrelated to the vector field over here. It just doesn't seem like it should be possible at all. But what we saw last time, and this is where we ended last time, is that if your vector field is a gradient, if you have a gradient field, then this always works. And there's a lovely little convenient, crisp, elegant little reasoning why, and that is, think about how you would compute these line integrals. Given that this vector field f is a gradient, we can use the fundamental theorem of line integrals. The fundamental theorem of line integrals for curve 1 is this. For curve 2 is this. And notice you get the same formula for each because they have the same starting point and same ending point. And when you use the fundamental theorem of line integrals, only the starting and ending point are involved. The formula literally only involves those 2 points. So, wonderfully elegant argument here, right? That immediately as a consequence of the fundamental theorem of line integrals, all gradient fields are path independent. So not only is it possible for a vector field to be path independent, it's not even all that rare, right? It's there's an entire category of such vector fields. Okay, all right. So wonderful little fact. Now, what we didn't have time to get to last time is that this also goes the other way. Not only is every gradient path independent, but every path independent is also a gradient. Exactly how to prove that requires a little bit of doing. It's not that bad. Here's a quick sketch. If you're curious, feel free to take a look. Not required for the course, but we don't have time to focus on it in class. But it's a clever little argument itself. Nice punchline for us is, as far as we're concerned, and I guess I should emphasize that there are regularity conditions, and I don't want to get bogged down with regularity problems in this course. Aside from regularity concerns, path independence and gradient, these are the same thing. Being a gradient is exactly the same thing as being path independent and vice versa. It's very, very cool. Okay. Alrighty. Now, here's a different way to say it. Seemingly, this is not going to be that big of a deal, but it turns out to be useful sometimes. So here's our shared starting point, shared ending point, curve 1, curve 2, right? And path independence means that I need for these two line integrals to be the same. Alternatively, that would be, really literally the same statement. I need their difference to be 0. All right, it means that their line integrals are the same. So, okay, but look at this. We could now consider what happens if I move along this curve that follows C1 and then just keeps on going, moving backwards along C2. Let's think about what is this line integral here on this sort of combined curve C. Well, that's going to give you exactly the line integral along C1 for the first part. And then, because you're going in the opposite direction, you're going to get the exact negative of the line integral along C2. So the point is, that integral is exactly that difference. So, when I say blue equals green, said differently, if I say green minus blue equals 0, well, green minus blue is red. That means the red integral is 0. So, this is that equivalent formulation. Totally equivalent formulation of path independence. A vector field is path independent if for all closed curves the line integral is 0. That makes sense to everybody? Not that different, but just kind of looks a little bit different. All right, so here's an example of how you can kind of see this in action. This is mostly a fun example. I don't know if any of y'all have ever seen the artwork of M.C. Escher before. You may have. It's pretty fun. It's what I like to think of as sort of geometric paradoxes, geometric impossibilities that are drawn to make it look like they're possible. It's a lot of fun. Right? I encourage you to take a look. This is one of them, one of his more well-known works of art. We'll get to that in a second. I want to start off by thinking about this vector field, what I like to call the steepness vector field. It's the gradient of the altitude function. Now keep in mind, if you're looking at the altitude function, you're keeping track of, height as a function of position. Maybe you're hiking in the mountains or what have you. If you want to know how much your altitude changes over a short distance, you do a dot product with the gradient. Right? So this gradient of the altitude function is a vector field that is a way of keeping track of how steep the mountain is and in which direction. And so it's just keeping track of how your altitude changes. Okay, so what can we say about this vector field? Well, it's clearly a gradient by definition. All gradients are path independent, as we just discussed on the previous page. And path independent means all closed line integrals are 0. Oh, real quick notational thing. This little circle, this little circle here in the middle of the integral symbol, that's just notation representing that it's a closed line integral. The curve starts and ends at the same point. Okay. All right. So, all closed line integrals are 0. Now, we know this about the steepness vector field, right, in previous discussions. Here's the thing. What Escher has done in this art, right, if you were to look at, as you kind of move along the stairs here, and let's just kind of look one little bit at a time, moving from there to there. Well, my altitude has increased. This fella, right? This person's altitude will increase a little bit as he climbs those stairs. So f dot dx will be positive, right? And then likewise, positive, 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 positive. These people following each other as you're going along here, they're all walking uphill, and so f dot dx is positive each step along the way. So as he's got it drawn here, he makes it look like, because all of these terms in the integral are positive, he's making it look like grand total, the altitude change in walking around that path is positive. But that's not possible, right? We just agreed, around a closed loop, line integral's got to be 0. Said differently, when you go on a hike and you start at a point, you go uphill, downhill, whatever you do, when you come back, your altitude's the same as when you started, right? So grand total, the altitude change must be 0. Escher's drawn it as if it is positive. That's the contradiction. That's the paradox, probably not quite the right term, but that's the nonsense that he's got encoded into the drawing. Does that make sense to everybody? So that's what makes this drawing interesting, is that it's a physical impossibility, but it looks real. All right, I think that's fun. Okay, let's see here. Moving along. So I claim that path independence is a really useful concept conceptually. Let me make a couple of quick comments about how is path independence useful as an idea. And I'm going to go back to what we said before about gradient fields. You may remember I pointed out that physicists like to use the term conservative. Why do they like to use the term conservative? It turns out that gradients are exactly the vector fields which, if they were representing forces, could be interpreted as relating as let's see how to say this. You can develop a corresponding notion of potential energy, and potential energy combined with kinetic energy. Again, if you've had a basic physics class, if you haven't, don't worry about any of this. Those two concepts together allow for the concept of conservation of energy, thus conservative for a vector field. Okay, so in order to be able to do this, though, what is it that we really need of the vector field? Why gradients? What is it about gradients that allows them to have this, that allows you to create a notion of potential energy? And it's actually a pretty simple idea. If I know what my potential energy is at one point, and I want to figure out what is my potential energy at some other point over here, I just have to ask, how much work does it take to go from this point to that point? And I just define the amount of work that it takes to do that to be how much potential energy increases between that point and this point. So, no problem, so it would seem, until you realize, what if I go along different paths? If I were to go along different paths and get different values of the line integral, then I would not have any way in which to define potential energy. So, why is it then that gradients allow for defining potential energy? It's because gradients are path independent. It's literally the path independence that allows you to say, yeah, sure, travel along whatever path you want. It doesn't matter. You're going to get the same amount of work anyway. So, perfectly well defined, completely independent of the path. So gradients can do this literally because of path independence. And what I think is wonderful about this argument is that it shows how, as a concept, path independence is really useful. You need that concept of path independence to be able to make the argument that I just made. Okay, so that's a digression. It's not critical to the course, but so to what extent is path independence useful computationally? I'm going to kind of argue that it's usually not. For example, let's think about what happens if you have a path-independent vector field. Well, among other things, I know that means that it's a gradient. Well, if it's a gradient, I can use the fundamental theorem of line integrals. So why do I need path independence then? Why do I need to develop this as an idea computationally anytime I can use it? I could also just use the fundamental theorem, which is a sledgehammer for vector line integrals. So, I mean, computationally we don't really need it. Think of path independence from a computational point of view as being a hammer. I already own a hammer. Once you already have one hammer, the value of a second hammer is much lower, right? If you have no hammers, a hammer is worth something. If you already have a hammer, how often do you need to go two-fisted with the hammers? It's not very common, right? So, there are some circumstances, though, when path independence still is actually useful. Now, this is going to be a suggestive of those circumstances, and then I'm going to criticize this example after I'm done. For the moment, let me just go on with it. Here's a vector field. I'm going to want to compute a line integral. Notice I'm given in the statement of the question that this is path independent. That's a given. I have a curve like so, and I want to compute this line integral over this given curve of this given vector field, which I am given is path independent. How am I going to compute this line integral? Well, look, we could plug and chug. Right? You can parameterize this curve, sines and cosines. Okay? You can take your sines and cosines, plug them into the vector field, take your sines and cosines, take the derivative. It's going to have more sines and cosines. You dot them, as the thing suggests. You end up with a lot of sines and cosines, and you can work out those sine and cosine integrals. And, you can do that, but trig integrals are a little annoying sometimes, and, all else being equal, we kind of prefer not to. Okay, so here's the better way to do this problem. we're going to use the fact of path independence. Right? Because of the path independence of this vector field, this given path independence, I can say, oh, well, all that really matters is the starting point and the ending point. And I don't really need this curve at all. It's path independent vector field. I can take any curve I want that starts and ends at the same points. So, you know what? I tell you what, I don't really like this green curve. This green curve's got trig all over it, and I don't want to deal with trig if I can avoid it. And I certainly don't have to deal with that curve. So I tell you what, I'm going to throw away that curve and now consider instead that curve. Starts at the same point, ends at the same point. It's going to give me the same value of this line integral. And it's a much more desirable curve. Look how easy it is to parameterize. Right? Super easy to parameterize. Nothing to it. Notice in particular also, no trig. Right? The trig has all disappeared. On this curve here, there's no trig in the parameterization. Of course, there never was any trig intrinsically in the vector field. And this turns into just a, what you might call a polynomial calculation, which of course is much easier than a trig calculation. So right off the bat, profit, right? We just benefited significantly from path independence. You just change the curve to a different curve that you like more. Okay, there's another advantage here. Notice that my new curve entirely on the x-axis, which means that y is exclusively 0. And there's something really nice about y being exclusively 0. If y is exclusively 0, dy is 0. The dy scalar coordinate differential. But also, if y is equal to 0, then this little y right here is 0, which means that top coordinate of the vector field is 0. Because all the points where I'm going to be computing this vector field, now that I've used path independence, they're all on this curve where y is literally 0. So that first coordinate disappears in a puff of smoke. And so not only is this algebra all polynomial, it's all just straight up, full on, actual 0. This dot product is just 0. I'm integrating 0. So this is not just an easier calculation, this is an easy calculation. And again, all of these benefits come out of the fact that I was able to change to a different curve, namely it comes out of capitalizing on path independence. How are we doing? Everybody with me? All right. Okay, so now let me criticize this example as promised. How come I didn't just use the fundamental theorem of line integrals? I'm going to give you a back and forth on that. Well, I was given the vector field, but you'll notice I was not given the antigradient. This is the gradient of something, but that something's not given, and I have not yet told y'all how to find antigradients. Now, I will at the end of today. We're going to get to it. But in this case, I don't immediately know how to find that antigradient. Okay, now the counter to the counter. Yeah, but we're gonna learn how to do this in a couple of minutes here. Couldn't we wait, 30 minutes until we learn how to find antigradients? And it'll be easy for this one. You could probably even kind of guess it just at a glance, right? Counter to the counter to the counter. True. This one is easy to find an antigradient, but there are examples kind of like this where they aren't. There are examples kind of like this where the vector field, finding the antigradient's going to involve some integrals. And sometimes those integrals are either undesirable or possibly even infeasible. Infeasible, unfeasible, not feasible. And in those cases, path independence. Awesome. Okay, enough of that. Okay, so how did I know that vector field was path independent? In the statement of this example, it's just given. No justification, right? Just, free information. So in practice, day in and day out, how do you know if a vector field is path independent? There's a lovely argument here. We're going to consider 2 dimensions. First, we'll get to 3 dimensions in a moment. But 2 dimensions first. Let me remind you, we already know that all 3 of these statements here are equivalent. Being a gradient means, among other things, that it's path independent. Being path independent means all closed line integrals are 0. Right, so we talked about that. All of this stuff we talked about earlier today. Okay. Now let me look at this bottom right condition. Notice this makes reference to closed line integrals. And let me remind you, Green's theorem addresses closed line integrals and says that all closed line integrals you can compute, regularity conditions aside, all closed line integrals you can compute as double integrals of Green's operator over the interior. So if I need all closed line integrals to be 0, that's effectively the same thing as saying all double integrals of Green's operator have to be 0. So that means that not only are these 3 conditions equivalent, but this 4th condition also equivalent. And it just kind of gets sucked into there by Green's theorem, saying that those integrals are the same. Okay, now let's look at this 4th condition here. And let's think about what that's telling me. Notice that this says not just that a double integral is 0. Notice this is any domain. It's any domain because it's what's inside of any closed curve. So this says for all 2-dimensional regions, the double integral of Green's operator is 0. So now just for a moment, let's ask, what can we say about this function here? This integrand, Green's operator. All double integrals of it are 0. All of them. Every set D. How could this be? How could there be a function where all of the integrals are 0? Every one of them. Can you think of any such functions? Double integrals always 0. And in fact, there really is only one, among continuous functions, there is only one actual example. And that is if the Green's operator function is itself flat 0. So, that's what then loops in the 5th condition. So these, we've now seen that these are all equivalent conditions. The big benefit here is with this statement right here. Notice that this is if and only if, so these are equivalent. And again, ignoring regularity issues, everything in sight is continuously differentiable. And so what that tells me, if I want to know if a vector field is a gradient, which of course I do want to know, very often I want to know, can I use path independence? Should I be hunting for an anti-gradient? Can I use the fundamental theorem of line integrals? These are all really important questions to know the answer to. The answer is compute Green's operator and see if you get 0. If you get 0, cool, you've got yourself a gradient. Go ahead and try to find the anti-gradient. It's out there somewhere. Yes, the vector field is path independent. Feel free to use path independence. Very nice. Very, very nice thing. So again, all you got to do, compute Green's operator, see if you get 0. By the way, a little bit of lingo. Keep in mind that Green's operator, just going back to several sections back, but what does Green's operator represent? And remember, I pushed this point of view, circulation density. Green's operator is a way of measuring to what extent is the fluid, in addition to moving, to what extent is the fluid maybe rotating, right? To what extent does the fluid have some sort of a spinning, rotational aspect to it? So, Green's operator is addressing the rotational aspect of the vector field. And for it to be 0 means that there is no rotational aspect to the vector field, and thus the term irrotational. So I think this is a great term. I'm a big fan. It communicates very explicitly this idea of Green's operator being 0 if you think again in terms of what Green's operator actually represents geometrically. Okay, how are we doing on that? Everybody with me? Yep.
Can you just explain again why intuitively makes sense that the Green's operator is 0, that it would represent the vector field being a gradient?
Well, so there's several steps in that process. If this integral is 0, if this operator is 0, well, that would tell me that this integral is always 0. But that would tell me that these line integrals are always 0 because, of course, the double integral of Green's operator is just a closed line integral around the boundary. And if closed line integrals are all 0, right? Closed line integrals are all 0, that means path independent. Is that cool? Yeah. All right. Okay. So, really nice fact. Now, all of this was in 2 dimensions. So, this theorem and this argument, all of this is specific to 2 dimensions. So, natural next question to ask, okay, what if we're in 3 dimensions? And, well, if you're in 3 dimensions, there is a highly analogous result and there is a highly analogous argument. And the only problem is that highly analogous argument uses something called Stokes' curl theorem, which we haven't talked about yet, and we'll get to that. Right? So for the moment, I can't prove this 3-dimensional analogous result, but I can state the 3-dimensional analogous result. And notice let me do it like this. If you want to know about whether something is or is not a gradient in 3 dimensions, notice that the role previously played by Green's operator is now just played by curl. So curl being 0 or not 0 tells you if a vector field is or is not a gradient. All right, let's do one. Let's get our hands dirty. By the way, I will give you all this argument when we get down to when we have all the appropriate tools. That'll be in chapter 7. Here we go. Here's a vector field, F. Notice this is a 3-dimensional vector field because it has 3 components. All right, always make sure to keep your eye on this, by the way. You don't want to apply 2-dimensional tools to a 3-dimensional vector field. It's a square peg round hole. It doesn't work, right? So you cannot talk about Green's operator on this vector field F. It's 3-dimensional. Green's operator is strictly 2-dimensional. So, is this vector field a gradient? And, well, we have our brand new theorem that says just look at the curl, see what you get. If you get exactly the 0 vector, then yes. Otherwise, no. So we start to compute the curl. The curl, of course, has 3 components as well. And make sure you remember the formula for curl. It's one of the few things in this course that I would say you have to actually really memorize. Most of what we have in this course are ideas to be understood. And if you really understand the ideas, the formulas kind of come along for the ride. But stuff like the formula for curl, you just have to have that memorized. So please make sure to lock that down. And here's the wonderful thing. Even after I compute just the first component of the curl, I didn't get 0. This first component, obviously, not identically 0. Well, if there is a coordinate that's not 0, then this cannot be the 0 vector. I don't even have to finish this calculation. Right? One coordinate has already messed it up for the other 2. This is not the 0 vector. So, therefore, this vector field is not a gradient. Is that cool? Everybody good? So don't waste your time trying to find an anti-gradient. This does not have an anti-gradient. You will fail. It's a wild goose chase. There's nothing to find. And also, don't even think about trying a path independence argument on this vector field. This is not a gradient, and so it is not path independent. So you can't use that tool either. Yes?
If the curl is 0, is it always path independent?
Yeah, if curl is, and again, I'm assuming regularity. So there's some really truly sticky wickets on this that I don't want to go on record online, on YouTube saying stuff that's technically not true. There are always regularity issues, and we're going to not worry about that in this course, right? But aside from regularity concerns, yes, if the curl is 0, then there is an anti-gradient, and it is path independent. Yep. All right. Okay, here's another example. Here's a vector field. We want to know if it's a gradient or not. Notice this vector field has 2 components. So this is a 2-dimensional vector field. And so we apply the 2-dimensional tool, namely we compute Green's operator. That's the tool for this question for 2 dimensions. And you punch it up and you get not 0. And when Green's operator is not 0, right, Green's operator not 0, then no, this is not a gradient. This is not path independent. Everybody all right? All righty. Now, here, just in case you are curious, here's a geometric point of view on this thing, on what we just talked about. This is a picture of that vector field. We've drawn this picture before, back in chapter 3, I guess it was. This is what I like to call the stirred pot, right? If you're looking at it from above, stirring the water in a pot as seen from above, stirring counterclockwise, this is how the water flows. Right? Ballpark. So let's think about this then. I claim there's kind of a connection to Escher stairs here. If this was actually a gradient, if these vector fields, if these field vectors were gradients, that means that these field vectors would all be pointing uphill, right? That's what gradients do. Gradients point uphill. And how could all of these arrows be pointing uphill? And it's just like the Escher stairs. These can't all be pointing uphill. You loop back around to where you were in the first place. You can't go up. Oh, look, now I'm back where I was. It just doesn't make any sense. It doesn't work. Right? So geometrically, you can see that this is not a gradient. But for those cases, majority of cases, of course, where you can't just look at the picture and see it, Green's operator does that work for us. Yeah.
Could we, on a test, make the geometric argument? And, how would we do that? Could we just write a couple sentences?
It's going to depend a lot on the phrasing of the question. The other problem with this geometric argument is it does... there's a lot of little details that I'm sweeping under the rug, right? So, for example, if I were to follow these field vectors, how do I know I would, in fact, get right back exactly where I started? How do I know I don't come back a little further to the right, in which case technically I don't have a contradiction. So there would be in this case, it'd be a problem, right? Whereas if you compute Green's operator and get not 0, done, right? There is no holes in that argument. I would say think about the geometric argument as being for intuition purposes, and on an exam, the geometric appeals tend to be risky. Yeah, good question. Okay, moving along. All right, so now this is what I call a strategic diagram. This is not in the book. Let me give you a couple of comments on where this comes from. So I've made some vague statements in the past about how a lot of the objects that we're dealing with in this course are actually kind of special cases of these more sophisticated things that we just can't go into. So for example, differential forms, right? And in particular, integrals of differential forms. Well, we can't cover that material in this class, but honestly, that's what a vector line integral is. And that's what a double integral on a two-dimensional region is in a different application. So anyway, a lot of the objects that we're talking about in this course actually are special cases of more sophisticated things. So there's another more sophisticated thing, couple of more sophisticated things. And these top two lines here, this is what I call diagram here, are kind of boiled down, formalities aside, no rigor, no precision, just structurally kind of preserving just what the upshot, right? The takeaways are of two of these more sophisticated things called chain complexes and co-chain complexes that, again, we can't cover in this course. So I claim, and again, details aside, it's really natural to compose these operators specifically in this order. And you may recall I made a vague reference to this back in chapter 3. And I talked about, among other things, the fact that this is an exact sequence. That means that everything has a lifetime of 2. And another way to say it is that if you have something here, and if you get 0 for Green's operator, then there is a function whose gradient is that vector field. Another way to say, or the other aspect of exactness, is that if you have a function and you take the gradient, thus giving you a vector field, Green's operator of that gradient field is 0. And so these are neat facts. These are strong, unexpected relationships between the gradient operator and Green's operator. And it's really nice to have those, to be aware of those. I personally find it easier to keep track of those by having this diagram and thinking, okay, well, we've got a 2-step diagram and everything survives for a lifetime of 2, and so then all this follows. Right? It's just a more kind of organized, visually satisfying, perhaps, way to think about these ideas. Okay, so I want to point out the same works with the boundary operator. And now, again, in defense from, there are some issues afoot here that I don't want to get in trouble for. So I'm going to say there's a sticky wicket on this. It can be dealt with. It's nothing y'all need to be concerned about. Y'all probably won't catch me on the mistake that I'm about to deliberately make, because I want to streamline this down to what you really in practice need. Right? So, nevertheless, asterisk, acknowledged. And with that said, boundaries make an exact sequence in the same way. For example, if you have a 2-dimensional region and you look at its boundary curve, think about an example, right? A 2-dimensional region in a 2-dimensional world. Think about that boundary curve. That boundary curve can't have endpoints. Said differently, the boundary of the boundary curve is always nothing. Right? That's just, geometric. I mean, here's an easy picture to draw. Here is a 2-dimensional region. Some lumpy 2-dimensional region. Here's the boundary curve. Where's that boundary curve start and end? Where's the starting point? Where's the ending point? Said differently, what is the boundary of that boundary? Nothing. It doesn't start, it doesn't end. It's a closed curve. Does that make sense from the picture? And then, by the way, vice versa. If you have a curve that's a closed curve, if it comes back around, that means that you think of it like a fence. That means that you've closed the fence. That means it will fence off an interior. In other words, it is the boundary of a 2-dimensional region. So, anyway, it's kind of nice geometry, nice fact of 2-dimensional geometry. Okay, so there's a lot of good stuff in this diagram. Like I say, it's a great way to organize ideas. We've got a bunch of stuff we've been doing. We've talked about the fundamental theorem of line integrals. I like to think about that as a statement that involves participants on this picture. And likewise, we've talked about Green's theorem. And it is a statement involving participants on this picture. Let me talk through how those look. I claim that there is a very strong similarity. When you look at how these theorems appear on this diagram, very strong relationship. Here we go. Fundamental theorem of line integrals. If I have some function if I take the gradient of it, right, which I do. Look at the fundamental theorem of line integrals. There's an f, and then in the integral there's gradient f. So if I take a gradient, likewise, if I look at a boundary, and again I do, I have a curve here, and I have to look at the boundary points A and B to apply the fundamental theorem. That's the starting point and the ending point. So, I take a function, compute the gradient, moving to the right. I take a curve, look at its boundary, moving to the left. And this computation and this computation give you the same answer. In other words, doing an integral of the vector field over the curve, like so, evaluating the given initial function at the boundary points, like so, fundamental theorem of line integrals says they're the same. So now just for kind of streamlining purposes, let me abbreviate that. I guess I should keep my colors consistent. This is the pattern that I claim represents what the fundamental theorem of line integrals looks like on this diagram as I've drawn it. And now let's go through the same process for Green's theorem. Now, geometrically, totally different theorem. It's got two-dimensional regions in it. It doesn't have gradient. It's got Green's operator. Everything's different. And yet, what the theorem says is if you have a vector field and you take Green's operator of it, right? If you have a two-dimensional region and you look at its boundary curve, then the line integral of your original vector field over the boundary curve versus the double integral of your Green's function on the given region, same. So, representing all of these players in this diagram, in this way, laid out exactly as such, has the shocking conclusion that it makes the fundamental theorem of line integral and Green's theorem look exactly the same. So that's an eyebrow raiser, I think. It's like, whoa, seriously? Whoa, they're completely different theorems. How is it that they play out on the diagram exactly the same way? Very surprising. Now, let me give you a brief, this for cultural purposes. How could it be that these two such different theorems look so much alike? And there's a great answer to this question. It turns out that these two theorems, totally different theorems, they're both special cases of a more powerful, more sophisticated theorem called the generalized Stokes' theorem. And it's something that we're not going to be able to talk about in this class. It's another one of these. It's one of these sophisticated conclusions that comes out of where the sophisticated construction that this diagram is a shadow of. Right? So anyway, I think it's important to realize that this is not a coincidence at all. The fact that these two seemingly very different theorems look exactly alike on the diagram is because they are literally special cases of the same theorem. Arguably, they're really kind of the same theorem. And being able to see that, being able to sort of see how that could be, is very much helped by thinking about all this stuff in terms of this diagram. And I don't know why my stylus is just getting bad at this point. Okay. All right. So various other cool things that you can do. Let's talk about this one. You may recall we talked about there were some special vector fields. We've been talking about these special vector fields today. Here's different ways to say them. Gradients. Right? This is what it looks like on the diagram for something to be a gradient. Irrotational. We just talked about irrotational means that the rotational aspect, namely Green's operator, is 0. Right? And then I have a way that I kind of like thinking of path independence, and this is just, I'm not proving anything here. This is just kind of for suggestive purposes. Path independence means if I have two curves that have the same boundary points, then I get the same value for the line integral. Now that, I don't know. That's how I like to draw it for sort of hand-waving purposes. So then I find it useful myself to have a diagrammatic visual, sort of a strategic visual to go along with the fact that these concepts are all the same. They're all simultaneous. I mean, as concepts, I suppose they're different, but in terms of what vector fields they refer to, all the same vector fields. Right. Okay. Real quick, I want to point out on Sakai, I have a bigger, cleaner, clearer version of this diagram that I just don't have space for in these notes, and it's in the Sakai site for our sections, just our set, not the big course one. It's in the resources section, and it's called diagram.pdf, and it's got all the same information that this has, but kind of stretched out and fleshed out just a little bit more. So I encourage you to take a look at that. Okay, strategically, oh, excuse me. Let me point out that the diagram actually gives you suggestions of how to solve problems if you interpret the diagram the right way. So let's suppose we've been asked to compute a line integral, for example. Now let me clean up my diagram here. Got a big mess to get rid of. Okay, so let's suppose I've been asked to compute a line integral. Well, there's the line integrals. So I can see right away that my two candidates, I mean, obviously I can parameterize and plug and chug, but my two candidates for better ways to compute the line integral are these two theorems here. And notice, if I were going to use the fundamental theorem of line integrals, well, I would need to take whatever curve I have, look at the boundary points, no problem, just look at the curve, see where the endpoints are. That's not an issue. But the issue is, I need to know, can I take my given vector field and oh, come on, stylus. Can I move backwards through this arrow? Can I find an anti-gradient for my vector field? So the diagram, by the direction that these arrows point, indicates where you're going to have a problem. Ooh, can I move backwards through an arrow? That I don't know. Maybe, maybe not. And it also suggests how to resolve that matter. If you want to know if you can move backwards through that arrow, go forwards to the right, see if you get 0 or not. Right? And that arbitrates the question. If you do get 0, then you can move backwards through the left arrow. So, right there in the diagram kind of suggests the answer. Okay. So I think this is good for a lot of stuff. I'm a fan. I hope you'll use the diagram. I'm probably going to be making reference back to this diagram on a regular basis, maybe the more fleshed out one that I have on the Sakai site. But anyway. Okay, so last thing, real quick, how do we find anti-gradients? This is actually pretty straightforward, as it turns out. If I want to know if a vector field is a gradient, okay, all I got to do is ask if the given coordinates can be partial derivatives. And of course, they have to line up like that. And that means that really all I have to do is find a function that satisfies these equations. These three partial derivative equations. AKA these three anti-partial equations. I just need to find a function f that's equal to all three of these anti-partials. That's kind of it. Now there's a twist. There is a little sticky relationship there. Let me remind you, the reason that these equations here are connected is because if I take a partial derivative here with respect to x, right? Take a partial derivative with respect to x, well then this turns into that, and that's how I know these are connected. But here's the thing. Any function of only y and z will go to 0. So for the same reason that when you take a single variable antiderivative, and you always have to say plus c at the end, Likewise, when you're taking a partial antiderivative, you have to put in what we call a partial constant. Something whose partial derivative is 0 doesn't have to be a straight up constant. It can be just any function of y and z in this case, because the partial's with respect to x. So that's the one little twist that you have to remember, is it's not quite right to say that this has to be a specific arbitrary antipartial. But it does have to be one of the partials, and this is the complete list of partials. So, likewise for the other coordinates, here's a quick example. Let's look at first coordinate. Take the x antipartial. Second coordinate. Take the y antipartial. Third coordinate. Take the z antipartial. Easy antipartials, and it's tempting to say, ooh, those are different. You can't have a function that's equal to all three of these. Right? But again, we got to account for the constants. Really, it's these that I need to all be equal to each other. And this I can do. X squared y is in all three of these lines. It's there, and then it's hidden as part of this C3 partial constant function of x and y. X squared y is a function of x and y, so that's okay. Right? And then likewise, xz is there and there and there. Right? And minus yz squared is there, and there. So sure enough, we have found a single function that is equal to all three of these things. So that's my antipartial. Everybody good? Yeah, question.
Shouldn't it be like a vector of 1, 3?
Shouldn't it what now?
Isn't it a vector?
No, the antipartial is a function. So let's see. Yeah. So what I've done here is I assumed I had a vector field. That's the PQR, and this is I've moved backwards and I've found the scalar valued function whose gradient is that vector field. Yeah. Yep. Cool. All right. Take a look at this example here. It's not a big deal. It's easy to read. I'm going to call us done with section 6.3. See y'all on Friday. Have a good one. Oh, yeah. Thank you. And stick around for attendance, please. And I'm sorry that I had